Welcome to the session. The same concept and the thyristor itself. We'll see the continuation of series and parallel connection. In the last session, I discussed what exactly series connection, what is the problem that is due to unequal static VI characteristics, then what is the remedy for that problem that I discussed. But in series connection itself, this concept is a series connection only. Not only the problem with the unequal voltage distribution due to unequal static VI characteristics, there is a problem with unequal voltage distribution due to unequal dynamic characteristics also. Okay, that I will discuss this concept as a case 2. Okay, in the same series connection itself, in the series connection, this concept is continuation of series connection only. The continuation of a series connection. Yes, a series connection itself. Okay, under this I am discussing case 2. Case 1 I already discussed. Go with the case 2. Then what is the cause? Cause is unequal voltage distribution. Unequal voltage distribution. Unequal voltage distribution is due to unequal dynamic characteristics. Yes, due to unequal dynamic characteristics. Unequal dynamic characteristics. This is the cause. Then remedy for this problem. Unequal voltage distribution due to unequal dynamic characteristics. Then what is the remedy for this problem? Well, you want to equalize the dynamic characteristics. That means what I am telling that even though SCRs with the same rating and same specifications, practically they don't have same dynamic character. A remedy later on I will give. Just 1 or 2 points I want to give with respect to cause. That is unequal dynamic characteristics. Even though SCRs with the same rating and same specification. For example, I am using 2 thyristors. 2 thyristors I am using. These 2 thyristors, let us assume that this is 500 volts thyristor and this also 500 volts thyristor. Okay. Both are 500 volts thyristors, but these 2 SCRs does not have same turn on time and same turn off time. What is the reason is, even though SCRs with the same rating and same specifications, why they don't have same dynamic characteristics means because of unequal charge distribution. For example, let one SCR is T1 SCR is under forward blocking mode. Okay, this is the T1 SCR is under forward blocking mode. Let J1 is closed, J2, J3 is closed, J2 is open. This is T1. Okay. Let us consider another one, that is T2 SCR. This is T2 SCR. Okay. This is T2 SCR. J1 is closed, J3 is closed, J2 is open. Both are same rating. But even though both the SCRs are same rating, the charge distribution at J2 junction in T1 SCR, then the charge distribution at J2 junction in T2 SCR may not be same, may not be equal. Whenever charge distribution is unequal at the junctions, we know that Q equal to IT, this equal to CV. If the charge distribution is changes, but the time is also changes. It may be turn on or turn off time. That's right. Unequal voltage distribution due to unequal dynamic characteristics. Now what I am telling, that is, even though SCRs with the same rating and same specifications, even though SCRs with same rating and same specifications, same rating, they don't have same dynamic characteristics. Same dynamic characteristics. Same dynamic characteristics in the sense T on and T off, due to unequal charge distribution. Unequal charge distribution across the junction. Charge distribution. Even though SCRs with the same rating, they don't have same dynamic characteristics due to unequal charge distribution. This is the reason why there exists unequal dynamic characteristics. Now, due to unequal dynamic characteristics, there exists unequal voltage distribution. Due to this unequal voltage distribution, sting efficiency reduces. Because of this unequal voltage distribution, sting efficiency is reducing. Now we want to equalize the voltage distribution. In order to equalize the voltage distribution, it is required to equalize the dynamic characteristics. Then how we can equalize the dynamic characteristics? That means I am discussing this concept as a remedy. Now what is the remedy for this problem? A remedy in the sense solution. That is, to equalize the dynamic characteristics, to equalize the dynamic characteristics, it is required to equalize, which one? Charge distribution. It is required to equalize the charge distribution. What is the reason for unequal dynamic characteristics? Because of unequal charge distribution. Then how to equalize the charge distribution? But another point here, Q equal to IT now. If Q is changes, what the capacitance offered by the junction is also. That means, that is, to equalize the dynamic characteristics, it is required to equalize the charge distribution, that is indirectly, that is capacitance distribution across the junction. Capacitance distribution, that is capacitance distribution across the junction. Now how to equalize? Let us consider n number of SCRs are connected in series and so on. If n number of SCRs are connected in series, each SCR offers different values of capacitances. That this is C1, this is C2, this is C3 and so on. If each SCR offers different values of capacitance, means to equalize the capacitance distribution across each SCR, we can connect different values of capacitors. This is SCR, this also SCR, this also SCR. Across each SCR, we can connect different values of capacitors. But practically it is a complex process now. Then for approximate equalization, one equal value of capacitance one equal value of capacitance is designed, that capacitance is connected across each SCR. Understood? That means to equalize the charge distribution, that means to equalize the dynamic characteristics, it is required to equalize the capacitance distribution. Then what I am doing here? For approximate equalization of not exact is not possible. Understood? For approximate equalization of capacitance distribution, for approximate equalization of capacitance distribution, for approximate equalization of capacitance distribution, okay, across each SCR, one equal capacitance is connected, one equal value of capacitance is connected, one equal value of capacitance is connected. But practically don't connect single capacitor. Always once we are connecting capacitor means in series with capacitor we can connect resistance also, because to limit the discharging current of capacitor. This RC combination across the SCR is also called snubber circuit or dynamic equalizing circuit. Yes, continuation. That means but practically don't connect single capacitor, don't connect a single capacitor across SCR. Why? The discharging current of capacitor may damage the SCR during turn on of SCR. That I discussed in the snubber circuit now. But practically don't connect single capacitor across SCR. Always a resistance is connected in series with capacitor. Always a resistance is connected. A resistance is connected in series with capacitor. In series with capacitance. The RC combination across the SCR is called. This RC combination across SCR is called. Which one? Tell me. This RC combination across SCR is called. This series RC combination. Across SCR. Across SCR is called. Is called dynamic equalizing circuit. Dynamic equalizing circuit or which one? Snubber circuit. Dynamic equalizing circuit or snubber circuit. This RC combination across SCR is called dynamic equalizing circuit or snubber circuit. Like this we can equalize the dynamic characteristics. Now the question is how to calculate this dynamic equalizing capacitance. Whatever the capacitance we connected in the dynamic equalizing circuit, that is called dynamic equalizing capacitance. Then how to calculate this dynamic equalizing capacitance? That I want to discuss. That we will see. Okay. Understood? Concentrate. If any point is not noted down, concentrate. Quick. Maximum, once I am explaining theory means maximum try to write in parallel. If any problem is solving or if any derivation is given, maximum time I will give. Okay. Once I am with explanation I am writing theory means parallel you write the theory. Okay. Then Concentrate. Calculation of dynamic equalizing capacitance. Dynamic equalizing capacitance. Okay, this you know. A RC combination across the thyristor is called dynamic equalizing circuit. Let us consider two thyristors only. This is let R1, this is C. This is R1, this is C. Then if you want to effectively utilize this circuit means to bypass the resistor during charging of the capacitor, what you can connect? Resistance. What you can connect? A diode is connected across the resistance. Okay. This total circuit is called which one? Dynamic equalizing circuit. This is called dynamic equalizing circuit. Then what is this circuit is called? This is R and this is also R. This is static equalizing circuit. Yes, this is static equalizing circuit. Where R1 is current limiting resistor. That consists in the dynamic equalizing circuit. Where C is dynamic equalizing capacitance. Dynamic equalizing capacitance. I want to calculate this. How to calculate this? That I want to explain. To calculate dynamic equalizing capacitance, this diode is connected. What is the purpose of connecting that diode? That I already explained. To bypass the resistor during charging of capacitor. To calculate dynamic equalizing capacitance. To calculate dynamic equalizing capacitance. Okay. Dynamic equalizing capacitance. Okay. Capacitance. Let us consider reverse recovery characteristics of thyristor. Reverse recovery characteristics of thyristor. Recovery characteristics of two thyristors. Let us consider reverse recovery characteristics of two thyristors. And these are the reverse recovery or turn off characteristics of two thyristors that I am drawing here. Okay. If that during turn off of thyristor, this characteristics is seen. Okay. Let the time taken for one thyristor is T1. The time taken for another thyristor is T2 during turn off. Okay. This is for T1 and T2 thyristor. Okay. Then This is the charge difference. This is the charge difference between the thyristors. Let this charge difference is taken as, or instead of these lines, take like this, sorry. Okay. Now this is for T1, one is for T1 thyristor, another for T2 thyristor. Okay. This is charge difference. Because of this charge difference only, we are getting unequal dynamic characteristics. Let this is delta Q, where delta Q is the charge difference between the two thyristors. Then because of this, let T1 thyristor takes the time of T1, T2 thyristor takes the time of T2. Then because of this charge difference, we are getting unequal turn of time. Let this is anode to cathode current. This I taken as a time axis. Okay. Now we want to calculate what is the capacitance is required to equalize this delta Q, to equalize this charge difference. What is the purpose of equalizing charge difference? If this charge difference is equalized, then the characteristics will be equalized. Once the characteristics are equalized, then both the SCRs blocks the same voltage. Then we can improve the string efficiency. Okay. Now because of this, let T1 blocks, voltage of V1, that equal to VBMX. I am assuming that T1 blocks the voltage of V1, that is VBMX. Then T2 blocking voltage. Then what is the blocking voltage of T2, you tell me? Then T2 blocking voltage, V2 equal to, what is the charge difference? This one. Because of this charge difference, the blocking voltage, it becomes how much? VBMX. Actually it blocks VBMX. Remaining voltage is blocked by V2 now. Then how much it blocks? Delta Q by VBMX minus delta Q by C. This much of voltage it blocks. Understood? Let us assume that two thyristors. If one SCR blocks VBMX, means because of the charge difference, V2 blocks this one. If this charge difference is not present, delta Q by C means Q equal to CV na, V equal to Q by C na. This also indicates voltage na. This difference of voltage it blocks. This is this one means this much of this. If it is 0, this charge difference is 0, then V2 is also same voltage. But it is not possible because of unequal charge difference, because of charge difference. This is V1. Same concept what I explained in the derivation of static equalizing resistance. I am assuming that T1 belongs to one category and remaining ns minus 1 SCRs are belongs to this category. Okay. Now let total string voltage is Vs. Let Vs equal to string voltage, total string voltage. String voltage. If ns number of SCRs are connected in series, if ns number of SCRs are connected in series, okay, then tell me what is the total string voltage? The total string voltage is equal to, I am assuming that one SCR blocks one voltage, VBMX. Remaining ns minus 1 SCR belongs to this category, that is ns minus 1 into what you get, VBMX minus delta Q by C. Okay, this you simplify, what you get, tell me. This is simplify. What do you get? Then Vs equal to VBmx plus Ns into VBmx minus VBmx plus Ns minus 1 into, this is minus Ns minus 1 into delta Q by C. Okay, this I am simplifying. This VBmx cancel now. Then Vs equal to Ns into VBmx minus Ns minus 1 into delta Q by C. Then what is Ns minus 1 into delta Q by C equal to? From this, I am writing this one. Vs equal to Ns into VBmx minus Ns minus 1 into delta Q by C. Yes? From this, what you can tell me? From this, what you can calculate? That is Vs equal to, this I am written like this now. Ns minus 1 into delta Q by C. Ns minus 1 into delta Q by C equal to, what do you get? Ns into VBmx minus Vs. From that equation I am writing. Last equation. Then from this, what is C equal to? Ns minus 1 into delta Q by Ns into VBmx minus Vs. This is the value of dynamic equalizing capacitance. What do you see here? Dynamic equalizing capacitance. Dynamic equalizing capacitance. This value of capacitance we can connect to equalize the dynamic character. What is delta Q? Charge difference. You remember this formula as a C equal to Q by V formula. C equal to Q by V formula. Yes, clear? From this equation, I written those two steps. Then I am getting C equal to Ns minus 1 into delta Q by Ns into VBmx minus Vs. This is the dynamic equalizing capacitance we can connect. This one. This is the dynamic equalizing capacitance we can connect in order to equalize the which characteristics? Dynamic characteristics. Okay. This about what exactly? Series connection. One problem in series connection is unequal voltage distribution due to unequal static VI characteristics. To equalize those characteristics, we are connecting the static equalizing resistance. What is that static equalizing resistance? That I already given. The another problem is in series connection itself, that is unequal voltage distribution due to unequal dynamic characteristics. Now you want to equalize the dynamic characteristics. To equalize the dynamic characteristics, we are connecting the capacitance. That is the dynamic equalizing capacitance. With this, in detail about series connection is complete. So any doubt? Concentrate on this one. No doubt? The derivation is there now. Note down that. Because of charge differences, that you are substituting. V2 equal to VBmx minus delta Q by. This is string voltage. Let Vs equal to string voltage. If Ns is number of SCRs are connected in a string, one SCR blocks this voltage, remaining Ns minus 1 SCRs blocks this voltage. Then what is the dynamic equalizing capacitance? That I calculate. I am writing in notes. A static equalizing circuit consists of, or the practical method of equalizing the static characteristics is connecting equal resistance across each SCR. Practical method of equalizing the static characteristics. Equalizing static characteristics is connecting equal resistance across each SCR. Equal resistance across each SCR. Across each SCR. That is the practical method we are doing. We don't connect different values of resistances. Okay. Then that means static equalizing circuit consists one equal resistance across each SCR. One equal resistance across each SCR. Okay. SCR with high leakage current. This I already given proof also. Explain that one. SCR with high leakage current. High leakage current. Blocks less voltage. Blocks less voltage. Next, third observation. SCR with high leakage resistance. SCR with tell me, high leakage resistance. High leakage. If the resistance is high means current is less. High leakage resistance. Blocks high voltage. Exactly opposite. Blocks high voltage. Okay? Blocks high voltage. Next. A dynamic equalizing circuit consists of a dynamic equalizing circuit. A dynamic equalizing circuit consists of which one? Consists of R and C in series and diode across R. This is what exactly dynamic equalizing circuit and diode across R. The another point to remember here, a snubber circuit is used, that I already given in terms of application also, but once again I am list out here. A snubber circuit is used. A snubber circuit is used. In the application point of view also I already explained in the summary. A snubber circuit is used to reduce dV by dt. Another one is this you've seen. Okay. To equalize which characteristics? Dynamic characteristics. To equalize dynamic characteristics. That you've seen how to equalize dynamic characteristics. Then last one. A dynamic equalizing capacitance is calculated based on which characteristics you tell me. A dynamic equalizing capacitance is calculated. A dynamic equalizing capacitance is calculated. Capacitance is calculated based on reverse recovery characteristics. Based on reverse recovery characteristics. Recovery characteristics. Okay, these points you remember as a final summary with respect to series connection. Also one formula means what the static equalizing resistance R equal to, as a summary I am giving, Ns into VBMX minus Vs by Ns minus 1 into delta IB. What is the dynamic equalizing capacitance C equal to Ns minus 1 into delta Q by Ns into VBMX minus V. Ns minus 1 into delta Q by Ns into VBMX minus Vs. As a summary, this I am giving. Always string efficiency is less than 1, that is practically. Ideally string efficiency equal to 1. Yes. Let us consider two number of thyristors are connected in parallel. Let us consider two number of thyristors are connected in parallel. Two number of thyristors are connected in parallel. Okay. Now, this is T1, this is T2. Let both the SCRs are having same rating and same specification. But even though SCRs with the same rating and same specification, practically they don't have same static VI characteristics. Okay, now I want to draw what is the static VI characteristics of both the SCRs. Here I am concentrating on parallel connection. Parallel connection in the sense current carrying capability, current sharing. Current sharing is possible under blocking mode or conduction mode. Conduction mode. We know that how to draw the static VI characteristics. But this indicates the conduction mode. How to draw the static VI characteristics, that you know. How to draw the static VI characteristics. This indicates conduction mode and this indicates blocking mode. But I want parallel connection now. That's why I concentrate only on conduction mode. I don't want to draw the characteristics of blocking mode. Now if you consider only characteristics of conduction mode, forward conduction mode characteristics. This is the characteristics of thyristor under forward conduction mode. This is anode to cathode current and this is anode to cathode voltage. Let two thyristors are conducting. I am considering only forward conduction mode characteristics. I am not considering the characteristics under blocking mode because I want current sharing only. Okay. Later, this is the characteristics of one SCR and this is the forward conduction characteristics of another SCR. Let this is T1 and this is T2. Next. Okay. This is the characteristics of two SCRs. If the SCRs are conducting means, there exists some voltage drop now. For same voltage drop, I am considering the same voltage drop. If the SCRs are conducting means there exists some voltage drop. Let the voltage drop of Vt. For same voltage drop, then T1 sharing the current of I1. Then T2 sharing the current of I2. That means even though SCRs with the same rating and same specification, practically they don't have same static VI character. Because of unequal static VI characteristics, there exists a unequal current distribution. This is I1 and this is I2. Let this current is I and this current is I. If the SCRs are conducting, there exists some voltage drop now. I am assuming that for same voltage drop, T1 sharing the current of I1, T2 sharing the current of I2. Therefore, because of unequal static VI characteristics, there exists an unequal current distribution. Now, due to unequal current distribution, what happening? Then you can define what is string efficiency. The string efficiency equal to current through the whole string, that is I1 plus I2 by number of parallel connected SCRs. How many number of SCRs we connected? 2. Individual current rating of each SCR. But here I1 is greater than I2 na, then you take I1, high value consider 2I1. Then this string efficiency is less than 1. That means string efficiency is reducing. That means what I am telling here, it is even though SCRs with the same rating and same specification are connected in parallel, practically they don't share the same current. Due to this, string efficiency is reduced. That is, even though SCRs with the same rating and same specification, same rating and same specification, and same specifications. Okay, are connected in parallel. Practically, they don't share the same current. Even the SCRs with the same rating and same specifications are connected in parallel. Practically, they don't share the same current. Due to which one? Due to they don't share the same current. Due to this, string efficiency is reducing. Now we want to improve the string efficiency. Then how to improve the string efficiency? Okay. This I will discuss in different cases. This concept I want to discuss in different cases. Okay. This concept I want to discuss in different cases. I will start with case 1. In parallel connection, I am discussing with case 1. Case 1 is, first one is unequal current sharing. What is the cause? Unequal current sharing. Due to unequal static VI characteristics. This is the cause. Unequal current sharing due to unequal static VI characteristics. Then what is the remedy for these problems? What is the remedy for this problem? Okay. One remedy is for DC circuit. That means if the SCR is operated with DC circuit in series with each SCR, for approximate equalization, not exact equalization, for approximate equalization, okay, in series with each SCR, one equal resistance is connected. One equal value of resistance is connected. One equal value of resistance is connected. Okay. That means you connect like this. These two thyristors are connected in parallel. Okay. This operating for DC, let us assume that this operating for DC. Yes, let this is the resistance R and this is the resistance R. This current is I1, this current is I2, this is VT1 and this is VT2. Then what is that resistance we can connect means? Can equate like this: I1 into R plus VT1 equal to I2 into R plus VT2. Now from this we can calculate R equal to VT1 minus VT2 by I2 minus I1. This much of resistance we can connect for approximate equalization of which characteristics? Current distribution. For approximate equalization of current distribution. If you want exactly equalize means you make this current difference is 0. If you want to make this current difference is 0 means you want to connect infinite resistance. That is meaningless. No? Understood? That's why for approximate equalization, once we are operating for DC circuit means how much resistance we can connect. This much of resistance we can get. This is under case 1 if it is connected, if it is operated in DC circuit. Similarly, if it is operated in AC circuits, what is the remedy we can use? Okay. That we will see in the continuation of this concept in the next session. And after that, in case 2, case 3, like that, so many cases I want to discuss in parallel connection. With that, parallel connection will be completed. Up to this, it's okay. Not possible exact equalization. If you want to make exact equalization, means you want to make infinite resistance. Not possible. Continue with the next section. You note down this.